Let us look at two interpretations of an asymmetric fold based on the same bed deep data and the seismic data. Consider seismic imaging of this portion. Here are the deep meter log data, and it shows that changing deep amount from these three to that one. Keeping that in mind, suppose an interpreter has made smooth folded layer. Now, in the other side we are finding changing deep direction. Not only that, from here to here we are finding the deep amount also has changed from gentle dip towards steep dip. This portion is to be extrapolated. Now, two approaches can be made, approach A, this one, and approach B. Consider we want to maintain same vertical time thickness. That means, this thickness has to be maintained as much as possible to be constant, the vertical thickness in one limb and the vertical thickness in another limb. Here it is bigger than limb, left limb. Call this limb as limb A, that limb as limb B. In case of possibility A, vertical thickness of limb A is nearly constant and vertical thickness of limb B is nearly constant, and there is no guarantee that limb A's vertical thickness and limb B's vertical thickness are equal. In fact, they are unequal as per this diagram. So, this can be one philosophy of extrapolation, and what we get is finally a thin limb fold. This limb, the orthogonal thickness is thinner than that limb. So, what we get finally is a thin limb fold. What does that mean? It means that orthogonal thickness in limb B is less than that of limb A. It is not that from this deep meter log data automatically this limb is produced. It is a part of a big work where only the summary is presented. This is a summary diagram. So, students, if they are trying from these deep meter log data and these deep meter log data to get into this conclusion, they will not be able to get. The entire work is not shown here. Now, here is the second interpretation where a constant thickness fold will be simulated. Again, from the data set that I have said and that is presented, you cannot create this diagram. For the entire work, you have to look at other publication which is referred here. Let us look at the constant thickness fold. In possibility B, where a constant thickness fold is created, the orthogonal thickness or the true thickness of the layers for limb A and limb B are maintained the same. Constant orthogonal thickness, or simply the thickness or the true thickness of limb A is same as that of. While we do that, the information provided by the deep meter log in terms of tadpoles is also followed. Note that from these tadpoles to those tadpoles, the deep direction has changed, and which is maintained in the diagram. Here this is the deep direction for these limbs, and for this limb and for that limb it is the deep direction. Note that the deep amount has significantly changed over here. So, we suspect this would be the region of the hinge of the fold, because in such drawing the deep amount here is much more than over here. So, this is point A and this is point B. The deep at B is less than the deep at A. So, where we find there is a low angle, this is the place of possibly the hinge. The same philosophy worked here. Here the deep angle is reduced, and so this is possibly a place where the layer is folded. both in possibility A and possibility B, if we measure the thickness over here, this thickness, the axial trace thickness is more than the orthogonal thickness. Here this thickness is more than this thickness. So, that we have not discussed, we have only measured the constant orthogonal thickness of the limb, that means we have exempted this portion. So, out of these two explanations, a geologist has to decide which one to take forward. The constant thickness fold or the parallel fold is the most common case in the fold thrust belts and is also most common for the post depositional folding. Therefore, this one is preferred. We prefer this particular interpretation. The different interpretations matter finally in choosing the drilling location. For example, suppose the target is to reach the core of the fold, then as per this drawing, this can be a suitable location to reach the core, and the drilling location is much shifted if we follow the constant thickness model, and here we can reach the core of the fold. We have discussed about the fault bend fold and the fault propagation fold. The reason was which model to choose finally also depends on in which kind of terrain we are working. We have said that post depositional folding is a case where this model is picked up. What if there is no post depositional folding? Let us say there is a syn depositional folding. Quick example can be a growth fault. Here I have drawn a listic normal fault, it is a growth fault, and the hanging wall block material is giving reverse drag and an antiformal structure which is known as the rollover anticline. The origin of growth fault is not well understood, but at least this much we can understand that there was more compaction of sediment in the hanging wall block than in the footwall block, and this rollover anticline was produced when faulting was happening, or more compaction of the hanging wall block material has happened. Therefore, the constant thickness fold model will not work in case of the growth fault, which can produce rollover anticlines, a product of the syn depositional folding. In this way, we have covered the prerequisites for cross section balancing. We have studied the strain parameters, the area calculation, we have looked at the fault related information, and we have also seen the fold geometry extrapolation and why it matters in hydrocarbon industries. Therefore, we are in a good position now to start the cross section balancing exercises. Cross section balancing is also known as restoration. Suppose an idol is broken, the idol can be restored. In the same way, restoration can be understood. A deformation has changed the lithological geometry, and what was the situation before deformation is attempted to find out, and that is known as the restoration. We are going to see progressively that it can be done by line length balance, area balance, and the volume balance. Line length balance is done for linear structures, area balance is done in 2-dimension cases, and the volume balance can be done with the 3-dimensional cases. Earlier, cross section balancing was performed in areas of contraction, compression, and the products were typically reverse faults. However, now routinely it is also applied on the extensional areas, so normal faults can also be restored. We can look at a folded layer, and by balancing we mean that its undeformed orientation generated either on paper or on computer screen. So, this is in the prototype, and this is the initial undeformed layer. This process of creating initial undeformed layer is known as restoration. We do this restoration on the cross sections. Therefore, This is also known as cross section balancing. There is an important point to note. There is no guarantee that a balanced section is always correct. That really this was the disposition may not always be true. Nevertheless, it does add validity to any interpretation. If we are able to find out deformed prototype to a reasonable initially undeformed layer, that means we have understood the deformation. This is one. The second point is the prototype has been properly documented or extrapolated. The third important point is if we know the initial undeformed layer position and the prototype, we know the deformation mechanism very well. This can give us a good idea about the zones of high and low pressure that led to deformation. If we know the zones of high and low pressure, then we can comment with more surety where hydrocarbon can be found within the structure, if at all it is present. So, the grand conclusion can be, it can give us a good idea about the drilling location and depths, the depth of drilling. So, in a simple way I have defined restoration, the term cross section balancing, why it is performed or why it is important, what can be the take home information from the cross section balancing exercises. Again, to proceed cross section balancing, a few terms are to be revisited. What is a plane strain? It is a deformation where along one direction no strain takes place. Consider a cuboid with dimension 8 centimeter multiplied by 2 centimeter multiplied by 7 centimeter. This is the initial undeformed condition. Suppose by a deformation the cuboid has attained length 16 centimeter, 1 centimeter, 7 centimeter. This is the deformed one. I mean to say, what was earlier 8 centimeter has become 16 centimeter, what was 2 centimeter has become 1 centimeter, and what was 7 centimeter has maintained the same length. If the direction where these were measured is x, if the direction where these were measured is direction y, and suppose this is the z direction, then we can see that along z direction no deformation has happened, and we can say that deformation has happened on the xy plane. Also we can see that in this situation it is a constant volume deformation, because 8 multiplied by 2 multiplied by 7 is equal to 16 multiplied by 1 multiplied by 7. So, no volume change has happened, no volume increase, no volume decrease has taken place in the cuboid. When it is a constant volume deformation, it is possible that along one of the directions, along z direction, there is no strain. Elongation is equal to the final length 7 centimeter minus the initial length 7 centimeter divided by the initial length 7, which is equal to 0. But along x axis there has been an increment in the length. So, along the x axis elongation has been final length minus initial length divided by initial length is equal to, in this case, is 1, and along the y axis the final length 1 centimeter minus initial length divided by the initial length is minus 0.5. A negative elongation means essentially a shortening. So, it is possible when there is a constant volume deformation along one of the directions there is no strain, whereas in other two directions along one axis there is extension, along another axis there is compression. But it does not guarantee that in all constant volume deformation plane strain condition can persist. Let us take another example. Consider a cuboid with volume 64 unit and along x axis the length is 8 unit, along the y axis it is 4 unit, and along the z axis it is 2 units. This is the undeformed situation. and after deformation the lengths got distributed in this way, 32 units, 2 units and then 1 unit. In this case it is a constant volume deformation and along axis x, y and z strain has happened. There is no axis along which no strain took place. So, this can indicate a condition which is not a plane strain condition. We also need to see a few simple cases. Consider a cuboid with dimensions x1, x2 and x3 along 3 directions. That means, x1 centimeter along direction 1, x2 centimeter along direction 2 and x3 centimeter length along direction 3, and that direction 1, direction 2 and direction 3 are perpendicular to each other. This is the undeformed condition. Suppose after deformation it still remains a cuboid and the lengths are x1 dash, x2 dash and x3 dash. Then the volume in the undeformed state is given by x1, x2, x3 and the volume in the deformed state is given by x1 dash, x2 dash, x3 dash. If it is a constant volume deformation, then volume u is equal to volume d, which means that x1, x2, x3 is equal to x1 dash, x2 dash, x3 dash. From this I can write x1 dash by x1 multiplied by x2 dash by x2 multiplied by x3 dash by x3 is equal to 1. Now, x1 dash by x1 is the final length divided by the initial length along direction 1. This is the final length divided by the initial length along direction 2, and this one similar thing for x3, which is same as stretch along direction 1 S1 multiplied by S2 multiplied by S3 is equal to 1. So, this is a special case. For S1, S2, S3 not equal to 1, it will indicate that the deformation is not constant volume. A similar deduction can also be made when one ellipsoid deforms to another ellipsoid. Consider ellipsoid E undeformed with the maximum principal axis 2x1, intermediate principal axis 2x2 and the least principal axis 2x3, and after deformation these amounts have changed to 2x1 dash, 2x2 dash and 2x3 dash. If it is a constant volume deformation, then the volume undeformed is given by 4/3 pi x1, x2, x3. x1, x2 and x3 are the semi major axis, semi intermediate axis and the semi minor axis, and the volume after deformation is given by 4/3 pi x1 dash, x2 dash, x3 dash. If the volume undeformed is equal to the volume deformed, we can write x1 dash by x1, x2 dash by x2 and x3 dash by x3 is equal to 1, and as I said earlier, these are the stretches S1, S2, S3. Since a sphere is a special kind of ellipsoid, what I have done for EU to ED, similar relation will hold true if it is EU to a sphere which is deformed or a sphere undeformed to an ellipsoid which is deformed. Consider a case that an ellipsoid undeformed by some deformation has become an ellipsoid which is deformed, and in this process there is x% volume loss. Then how much is S1 multiplied by S2 multiplied by S3 is a question for the students. And a similar problem, suppose there is a cuboid undeformed and after deformation it still is a cuboid and which is deformed, no rotation has happened in this case and in that case, and here there is y% volume gain, then how much is the product S1, S2, S3? If you do these things and later on if you put x equal to 0, no volume loss, or in this case y equal to 0 or no volume gain, you will go back to the expression that I have already done, S1 S2 S3 is equal to 1 in both the cases. This remains as your compulsory work